All right. So let's kick things off here with just a simple introductory question. So could you give us a little bit of background about SilverLining and what is its mission?
Sure, Lucas. And I want to start by thank you for inviting me to talk with you and your community, because the issue of existential threats is not an easy one. And so our approach at SilverLining, I think, overlaps with some of the kinds of dialogue that you're having, where we're really concerned about this sort of catastrophic risks that we may have with regard to climate change in the next 10 to 30 years. So SilverLining was started specifically to focus on near-term climate risk and the uncertainties we have about climate system instability, runaway climate change, and the kinds of things we don't have insurance policies against yet. So my background is from the technology sector. I worked in areas of complex systems analysis in IT infrastructure. And so I came into this problem looking at it primarily from a risk point of view, and the fact that the kind of risks that we currently have exposure to is an unacceptable one. And so we need to expand our toolkit and our portfolio until we've got sufficient options in there that we can address the different kinds of risk that we're facing in the context of the climate situation. So SilverLining is a 2-year-old organization, and there are 2 things that we do. We look at policy and sort of driving how, in particular, these interventions in climate, these things that might help reduce warming or cool the planet quickly, how we might move those forward in terms of research and assessment from a policy perspective, and then how we might actually help drive research and technology innovation directly. And so we do both of those things.
Okay, so the methods of intervention are policy and like research.
So our methods of operation are policy research. The methods of intervention in particular that I'm referring to are these sort of technologies and approaches for directly and rapidly reducing warming in the climate system.
Yeah, so I was also a bit surprised that so in what you just said, you mentioned that you're concerned about catastrophic risks from climate change, for example, in the next 10 to 30 years. Could you paint us a little bit of a picture about why that kind of time scale is relevant? I think many people, and myself included, might have thought that the more significant changes would take longer than 10 to 30 years. So what is the general state of the climate now and where we're heading in the next few decades?
Well, so I think there are a couple of key issues in sort of the evolution of climate change and what to expect and how to think about risk. One is that the projections that we have, it's a tough type of system and a tough type of situation to project and predict. And there are some things that climate modelers and climate scientists know are not adequately represented in our forecasts and projections. So a lot of the projections we've had over the past 10 or 15 years talk about climate change through 2100, and we see these sort of smooth curves of, depending on how we manage greenhouse gases, we've got these smooth curves. But people who are familiar with the climate system itself or complex type systems problems know that there are these non-linear events that are likely to happen. And right now in climate models, they have a very difficult time representing those. So in many cases, they're either sort of roughly represented or excluded entirely. And those are the things that we talk about in terms of abrupt change and tipping points. So our climate model projections are actually missing or underrepresenting tipping points. Things like the release of greenhouse gases from permafrost that could happen suddenly and very quickly as the surface melts. Things like the collapse of big ice sheets and the downstream effects of that. So one of the concerns that we have in SilverLining is that some of the things that tech people know how to do is a similar problem to manage an IT network. It's a highly complex systems problem where you're trying to maintain a stable state of the network. And some of the techniques that we use for doing that have not been fully applied to looking at the climate problem. And similarly, some of the similar techniques we use in finance. One of our advisors is the former director of global research at Goldman Sachs. And this is a problem we're talking to him about, and folks in the IPCC and other places, about, essentially we need some new and different types of analysis applied to this problem beyond just what the climate models do.
Right.
And so problem number one is that our analytic techniques are underrepresenting the risk, and particularly potentially risk in the near term. The second piece is that these abrupt climate changes tend to be highly related to what they call feedbacks, meaning that there are points at which these climate changes produce effects that either put warming back in the system or greenhouse gases back in the system, or both. And once that starts to happen, the problem could get away from us in terms of our ability to respond. Now, we might not know whether that risk is 5%, 10%, or 80%. From SilverLining's perspective, from my perspective, any meaningful risk of that in the next 10 to 30 years is an unacceptable level of risk, because it's approaching somewhere between catastrophic and existential. And so we're less concerned about the arm wrestle debate over, well, is there some scenario where we can constrain the system by just reducing greenhouse gases? We're concerned about, are there scenarios where that doesn't work? Yeah. And it appears that there's a meaningful probability that there are scenarios where the system moves faster than we can constrain greenhouse gases. And the final thing I'll say is that we're seeing evidence of that now. So some of the things that we're seeing, like these extraordinaries of wildfire events, what's happening to the ice sheets, these are things that are happening at the far end of bad predictions. So they're happening, the observations of what's happening in the system are indicative of the fact that risk could be pretty high.
Yeah, so you're ending here on the point that, say, the fires that we're observing more recently are like showing that tail end risks are becoming more common, and so they're less like tail end risks and more like becoming part of the central mass of the Gaussian curve.
That's right.
Okay, and so I want to slow down a little bit because I think we introduced a bunch of like crucial concepts here. So if you were to, so one of these is like tipping points. So if you were to explain tipping points in like 1 to 2 sentences to someone who's not familiar with climate science, how would you do that?
Well, the metaphor that I like to use is similar to a fever in the human body. And so warming heat acts as a stressor on the system, on different parts of the system. So when you have a fever, you can carry a fever up to a certain point, and if it gets high enough and long enough, different parts of your body will be affected, like your brain, your organs, and so on. And so the trapped heat energy in the climate system acts as a stressor on different parts of the system, and they can warm a bit over a certain period of time, and they'll recover kind of their original state. But beyond a certain point, essentially the conditions of heat that they're in are sufficiently different than what they're used to, that they start to fundamentally change. And that can happen in biological systems where you start to lose animal species, plant species. That can happen in physical systems where the structure of an ice sheet starts to disintegrate. And once that structure breaks down, it doesn't come back. Forests have this quality too, where if they get hot enough and dry enough, then they may pass a point where their operation as a forest no longer works, and they collapse into something else, like desertification. Right. And so there are two concerns with that. One is that we lose these big systems permanently because they change a state in a way that doesn't recover. And the second is that when they do that, they either add warming or add greenhouse gases back into the system as well. Mm-hmm. So when an ice sheet collapses, for example, these big ice structures, they reflect a huge amount of sunlight back out to space. And when we lose them, they're replaced by dark water. And so that's basically a trade-off from cooling to warming. that's happening with ice. And so there are different things like that where that combination of losing that system and then having it really change the balance of warming is a double faceted problem.
Right. So it's like you have these dynamic systems which play an integral part in maintaining the current climate stability, and they can undergo like a phase state change. Like water is water until you hit a certain degree, and then it turns into ice or it evaporates and turns into steam. Except you can't go back easily with these kinds of systems. And once it changes, it throws off the whole like more dynamic context that it's in, that's stabilizing the environment as we enjoy it. Did you want
That's
to react to
right.
that?
And I can throw up a picture for you.
Yeah.
This comes from Will Steffen, who is one of the fathers of Earth system science. And so one of the problems that you have is not just that any one of these systems might change its state and might start putting warming or greenhouse gases back into the atmosphere, but they're linked to each other. And so then they call that the cascade effect, where one system changes its state and that pushes another system over the edge. And that pushes another system over the edge. And so a collapse of ice sheets can actually accelerate the collapse of the Amazon rainforest, for example, through this process. So it's and that's where we come more towards the sort of existential category, where we don't want to come anywhere near that risk if we can help it, and we're dangerously near it, if not having some of these things start to happen already. And so I was trying to move this forward, but, and so one of the problems that, scientists like Will Steffen and some Arctic scientists, for example, are seeing is that some of these tipping points they think we're in. And I work with climate scientists really closely, and I hear them saying, we may be in it. Meaning that some of these tipping points are starting to occur. And so the ice ones, we have front page news on that today. The forest ones we're starting to see. And so that's where the concern becomes that we sort of lack the measures to address these things if they're happening in the next, 1, 2, or 3 decades.
Yeah, so we have so we have tipping points, which are, like we have dynamic systems which help to maintain the current state, like the equilibrium of the environment. And these like dynamic environments, like you just mentioned a bunch of them, like the ice caps and like the Amazon rainforest and all these things, they can undergo tipping points where they are irreversibly changed, or not irreversibly changed, but it would take way more energy and effort to put them back the way that they were. And then that leads to tipping cascades, where the failure of one system can lead to it can act as a catalyst for the failing of further systems. And then this becomes, I don't know, is this where a word like runaway climate change becomes relevant?
Yes. And so when I came into the space like 12 years ago, and for many of your listeners, I came in from tech first as a sort of area of passion interest. And one of the first people I talked to was a climate scientist named Steve Schneider, who was at Stanford at the time. And he's since passed away, but he was a giant of the field. And I asked him kind of the question you're referring to, which is, how would you characterize the odds of runaway change within our lifetime? And he said, at that time, which was about 12 years ago, he said, I put it in the single digits, but not the low single digits. And my reaction to that was, if you had those odds of winning the lottery, you'd be out buying tickets.
Yeah.
And if we had an 8 to 10% chance of an asteroid hitting the planet, we'd be building the giant laser array. And that's an unacceptable level of risk where we don't have responses that really meaningfully arrest or reduce warming in that kind of time.
Right. Okay, and so another point here is you've used the word existential a few times here, and you've also used the word global catastrophic. Now, I think broadly within the existential risk community, at least like the place where I come from, climate change is not viewed as an existential risk. Like even if it gets really, really, really bad, it's hard to imagine ways in which it would kill all people on the planet, rather than like make life very difficult for most of them and kill like large fractions. And so it's generally viewed as a global catastrophic threat, being that it would kill large fractions but not be existential. What is your reaction to that, and how do you view the use of the word existential here?
Well, so for me, there are two sides to that question.
Mm-hmm.
And I normally stay on one of the two sides, which is really about, for SilverLining, our mission is to prevent suffering.
Okay.
And so the loss of, you know, a third of the population of the planet or 2/3 of the population of the planet,
Mm-hmm.
and the survival of some people in interconnected bubbles, which I've heard top analysts talk about. For us, that's unacceptable. That's an unacceptable level of suffering and an unacceptable outcome. And so in that way, you know, the debate about whether it's all people or just lots of people is for us not that material, because that whole situation seems to be, you know, not a risk that you want to take.
Mm-hmm.
In the sense, in the other side of your question, whether is it all people and is it like planetary livability, I think that question is subject to this, some of the the inability to fully represent all of the systemic effects that happen at these levels of warming. And you know, early on when I talked about this with the director of NASA Ames at the time, who's now at Planet Labs, what he talked to me about was the changes in chemistry of the Earth system. And so, you know, this is something that it hasn't maybe been explored that widely, but we're already looking at collapses of life in the ocean. And between the ocean and the, you know, the land systems, that generates a lot of the sort of atmosphere that we're familiar with and that's comfortable for people. And there are risks to that we can't have these collapses of biological life and necessarily maintain the atmosphere that we're used to. And so I think that, again, I'll say that I think that it's inappropriate to discount the possibility that the planet could become largely unlivable at these higher levels of heat. And that in a runaway climate change scenario where the heat levels get very high
Mm-hmm.
and biological life collapses in an extreme way, I don't think that's been analyzed well enough yet. And I certainly wouldn't rule it out as an existential risk. I think that would be inappropriate given both our level of knowledge and the fact that we know that we have these sort of nonlinear cascading things that are going to happen. So to me, I challenge the existential threat community to look into this further.
Excellent. Yeah. Uh-huh.
Put it out there.
Yeah. Cool. I like that. Okay, so given like tipping points and like cascading tipping points, you think there's a little bit more uncertainty over how unlivable things can get.
I do, and that's before you also get into the societal part of it, right?
Yeah. So
the
how it can
of the subset of people that are left.
Yeah.
So I think it's, you know, going back to what I think has been one of the fundamental problems of the climate debate is this idea that there are winners and losers, and that this is a reasonably survivable situation for a certain class of people.
Mm-hmm.
I think there's a reasonable probability that that's not the case. And this is not going to be a world that anyone, if they do get to live in it, is going to enjoy.
Yeah, even if you were a billionaire back before climate change and you have your nice stocked bunker, it's
in New Zealand, yeah.
you can't keep stocking it. Your money won't be worth anything.
Yeah, and in a world without strawberries and lobsters and rock concerts and all kinds of things that we like. So I think we're much more in it together than people think, and that the humans were over the course of many millennia engineered and fine-tuned to this beautiful, extremely complicated system that we live in. And we're pushing it, we can use our technology the best of our ability to adapt, but really, this is an environment that's beautifully made for us, and we're pushing it out of a state that supports us.
Mm-hmm. Okay, so I'd be curious if you could expand just probably like fairly briefly here on, I'm curious to know like more of the ways in which these systems which help to maintain the current climate status like function. So for example, like the jet stream and the boreal forest and the Amazon rainforest and the Sahel and the Indian summer monsoon and the permafrost and all these other things. If you could choose, I don't know, maybe one or two of your favorites or something, or whichever few are like biggest. I'm curious how these systems like help continue to maintain the like climate stability.
Well, so, there are people more expert than me, but I'll talk about a couple that I care about a lot. So one is the permafrost, which is the frozen layer of Earth. And that frozen layer of Earth is on the surface in land masses, and also frozen layers under the ocean. And so for many thousands of years, if not longer, those layers, sort of they capture and build up like the biological life that's died and sort of decayed within these frozen layers of Earth, and stored massive amounts of carbon. And so provided the Earth system is working, within its usual parameters, all of those masses stay frozen. Mm-hmm. And that organic material stays there. And so as it warms up, in a way that it moves beyond its normal sort of range of parameters, then that stuff starts to melt and those gases start to be released. And so and the amount of gas stored in the permafrost is massive. And particularly it includes both CO2 and the more dense, fast-acting gases like methane. And so that, we're kind of sitting on the edge of that system starting to melt in a way where those releases could be massive. And in my work, that's, to me, one of the things that we need to watch most closely, because that's a potential runaway situation. So that's one, and that's a relatively straightforward one, because it's, a system storing greenhouse gases, releasing greenhouse gases. They range in complexity. Like the Arctic is a much more complicated one because it's related to all the physics of the movement of the atmosphere and ocean. So the circulation of the way the jet stream and weather patterns work, the circulation of the ocean, and all of that. So there could be potential drastic effects on what weather is where on the planet. So major changes in the Arctic can lead to major changes in what we experience as like our normal weather. Yeah. And we're already seeing this start to happen in Europe. And that was predicted by changes in the jet stream, where Europe's always had this kind of mild, sort of temperate range of temperature. And they're starting to see super cold winters and hot summers. And that's because the jet stream is moving.
I see.
And a lot of that is because the Arctic is melting.
Okay.
So I can give you another one if you want.
Yeah, I mean,
a personal one that's that's dear to me, and it is actually happening now, and we may not be able to stop no matter what we do, are the coral reefs. Mm-hmm. And so, coral reefs are these organic structures, and they teem with all different levels of life. And they trace up to about a quarter of all life in the ocean. So as these coral reefs are getting hit by these waves of hot water, they're dying. And ultimately, their collapse will mean the collapse of at least 25% of life in the ocean that they support. And we don't really know fully what the effects of that will be.
Mm-hmm.
So those are a few examples.
I see. So the hot waters, feel like I've heard the word heat stress before in relation to coral reefs, and then that's what kills it.
Yep.
They don't like functioning, and they can't function in hot water.
Right.
All right. So before we move into your specific proposed, the area you're interested in intervening as a potential solution if we can't get the greenhouse gases down enough. Are there any more bad things that we missed, or bad things that would happen if we don't sufficiently get climate change under control?
So I think that there are many, and we haven't talked too much about what happens on the human side.
Mm-hmm.
So there are even thresholds of direct heat for humans.
Mm-hmm.
You know, you've heard about this before, like the hot bulb temperature.
The what? Sorry?
The hot bulb temperature.
I
like
have not heard that.
The
before.
outdoor heat threshold for people.
Okay, what is that?
And I'm not going to be able to describe it super expertly, but the combination of heat and humidity at which the human body changes the way it's sort of expiring heat and sort of that heat exchange. And so what's happening in certain parts of the world right now, like in India, in parts of India, like Calcutta, there's an increasing number of days of the year where it's not safe to work outside. And there are some projections that by 2030, there would be no days in Calcutta where it was safe to work outside. And so the issue it becomes, and we even see parts of the US where you have these heat warnings. And right now, as a direct effect on humans, I just saw a study that said the actual heat index is killing more people than the smoke from fires. And so the actual increase in heat is moving past where humans are actually comfortable living and interacting. Now, as a secondary point, obviously in developed countries, we have lots of tools for dealing with that in terms of our, infrastructure. But one of the things that's happening is the system is moving outside the band in which our infrastructure was built. And this is a bit of an understudied area in terms of, as warming progresses and you have extreme temperature, you have more flooding, you have extreme storms and winds. We have everything from bridges to nuclear plants to skyscrapers that were not engineered for those conditions. They're moving outside the conditions that our infrastructure was built to. And so, full evaluation of that is not really available to us yet. And so I think we may be underestimating even things like, okay, in some of these projections, we know that as sea level rise happens and extreme storms happen, places like Miami are probably lost. And in that context, what does it mean to have a city the size of Miami sitting underwater at the edge of the United States? It would be a massive environmental catastrophe. Just that.
Yeah.
So I think unfortunately, like we haven't looked closely enough at what it means for all of these parts of our like human infrastructure, for their external circumstances to be outside the arena that they were engineered for.
Yeah, so natural systems become stressed, they become to fail, there could be cascades, human systems and human infrastructure becomes like getting stressed. I mean, you can imagine like nuclear facilities and oil rigs and whatever else can cause massive environmental damage, getting stressed as well by being moved outside the normal bandwidth of operation. So it just seems it's just a lot of bad things happening after bad things after bad things. Yeah.
Yeah, and you know, a big problem, because I've had this debate with people who are bullish on adaptation, that, you know, hey, we can adapt to this, but the problem is you have all these things happening concurrently. You know, they're happening at the same time. So it's not just Miami, it's Miami and San Francisco and Bangladesh. You know, it's going to be happening, lots of different variants of it happening all at the same time. And so anything we can do to prevent that, you know, excuse my academic language, shit show, is really something we should consider closely and invest in closely, because the cost of that and the sort of compound damage is just, it's pretty staggering.
Yeah, it's often much cheaper to prevent risks than to deal with them when they come up and then clean up the aftermath. So as we try to avoid, you know, moderate to severe or whatever bad effects of climate change we can mitigate, I think most everyone is very familiar with the idea of reducing greenhouse gas emissions. So the kinds of gases that help trap heat inside of the atmosphere. Now you're coming at this from a different angle. So what is the research interest of SilverLining, and what is the intervention of, you know, mitigating some of the effects of climate change? Yeah, what is that intervention that you guys are exploring?
Well, so our interest is in the near-term risk. And so therefore we focus most closely on things that might have the potential to act quickly to substantially reduce warming in the climate system. And the problem with greenhouse gas reduction and a lot of the categories of emerging category of removing greenhouse gases from the air are that, you know, they're likely to take many decades to scale, and even longer to actually act on the climate system. And so if we're looking at sub 30 years, where we're coming from in SilverLining is saying, we don't have enough in that portfolio to make sure that we can keep the system stable. And so I'm going to share my screen with you again. Yeah. We are a science-led organization, meaning we don't do research ourselves, but we follow the recommendations of the scientific community and the scientific assessment bodies. And in 2015, the National Academy of Sciences in the United States, they ran an assessment that looked at the different sort of technological interventions that might be used to accelerate addressing climate warming and greenhouse gases. And they issued 2 reports, one called Climate Intervention, Carbon Dioxide Removal, and one called Climate Intervention, Reflecting Sunlight to Cool Earth. And what they found was that in the category where you're looking to reduce warming quickly within a decade or even a few years, that the most promising way to try to do that is based on one of the ways that the Earth system actually regulates temperature, which is the reflection of sunlight from particles and clouds in the atmosphere. So that's what you're seeing here is a simulation from NASA of the movement of clouds and particles in the atmosphere and the reflection of sunlight. And the theories behind why they think this might work are based on observations from the real world. And so what I'm showing you right now is a picture of a cloud bank off the Pacific West Coast, and the streaks in the clouds are created by emissions from ships. And so the particulates in those emissions, usually what people think of as the dirty stuff, has a property where it often mixes with clouds in a way that will make the clouds slightly brighter. And so based on that effect, scientists think that there's cooling that could be generated in this way actively, and also that there's actually cooling going on right now as a result of the particulate effects of our emissions overall. And they think that we have this accidental cooling going on somewhere between 0.5 degrees and 1.1 degrees C. And this is something that they don't understand very well, but is potentially both a promise and a risk when it comes to climate. So this approach is.
Can we go back for a second?
Sure.
Yeah. So like there's like some amount of cooling that's going on by accident, but
Right.
the last bar is showing that the net anthropogenic heating is positive even with the cooling. And I think one facet of this that I learned from looking into your work is that the cooling effect is limited because the particles fall back down, and so it goes away. And so there might be like a period of acceleration of the heat. Is that right?
So yes, I think what you're getting at. So two things I'll say. These white lines, sort of spider lines, indicate the uncertainty. And so you can see the biggest line is on that cloud albedo effect, which is how much do these particles brighten clouds. And so the effect could be much bigger than what's going into that net effect bar, and a lot of the uncertainty in that net effect bar is coming from that one thing.
Mm-hmm.
So,
coming from whether or not they fall?
Coming from this cloud albedo effect, uncertainty of what is that magnitude of the effect. Now, the fact that they fall is an issue, but what happens today, for the most part, is we keep putting them up there. And so as long as you continuously put them up there, you continuously have this effect. If you take it away, that's the next picture, which we're doing a couple of big experiments in this year, then you lose that cooling effect right away. And so one of the things that we're hoping to help with is getting more money for research to look at two big events that took that away this year. One is the economic shutdowns associated with COVID, where we had these clean skies all over the world because all this pollution went down. And so that's a big, global experiment in removing these particles that may be cooling. And so we are hoping to gain a better understanding from that experiment if we can get enough resources for people to look at it well.
So the uncertainty with how much, like the degree to which current pollution is reflecting sunlight, is that because we have uncertainty over like exactly how much pollution there is and how much sunlight that is exactly reflecting, given the amount of, do we just not know how much like a certain size cloud reflects sunlight?
It's not that we don't know how much pollution there is. I think we know that pretty well. It's that this interaction between clouds and particles is one of the biggest uncertainties in the climate system. And there's a natural form of it, like when you see salt spray generating clouds, like you're in Big Sur looking at the waves and the clouds starting to form. That whole process is highly complex. Clouds are among the most complex creatures in our Earth system. And so, and they're based on the behavior of these tiny particles that attract water to them and then create different sizes of droplets. So if the droplets are big, they reflect less total sunlight off less total surface area, and you have a dark cloud. And eventually the droplets are big enough, they fall down as rain. If the droplets are small, there's lots of surface area, and the cloud becomes brighter. And so the reason we have that uncertainty is that we have uncertainty around that whole process. And some of the scientists that we work with in SilverLining, they really want to focus on that, because understanding that process will tell you what you might be able to do with that artificially to create a brightening effect on purpose, as well as how much of an accidental effect we've got going on.
Okay.
And
go ahead.
Well, you go ahead and then I'll...
Yeah, sorry. The last thing was just, so you're saying we're removing sulfate from the emission of ships, and sulfate is helping to create these sea clouds that are reflecting sunlight.
That's right. Yeah. And it happens over land as well, right? So it's all the emissions that contain these sulfate and similar types of particles can have this property.
And so that plus the reduction of emissions given the reduction of pollution given COVID, there is this ongoing experiment, an accidental experiment to decrease the amount of reflective cloud.
Yeah, that's right. And I should just note that the other thing that happened in 2020 is that the International Maritime Organization implemented regulations to drastically reduce emissions from ships. And so those went into effect in January, an 85% reduction in these sulfate emissions. And so that's the other experiment.
Because sulfate
And these emissions we don't like as pollutants for human health, for local ecosystems. They're dirty, they're really vile. So we don't like them for very good reasons, but they happen to have the side effect of producing a brightening effect on clouds. And that's the piece we want to understand better.
Okay. Happy to move on.
Yeah, when I talk to especially people in the Bay Area and people who think about systems, about this particular dynamic, most of the people that I've talked to are unfamiliar with this. And lots of people, even who think about climate a lot, are unfamiliar with the fact that we have this accidental cooling going on, and that as we reduce emissions, we have this uncertain near-term warming that may result from that, which I think is what you were getting at.
Yeah. So, okay. Yeah, let's keep going.
So where I'm headed with this is that in the early 90s, some British researchers proposed that you might be able to produce an optimized version of this effect using sea salt particles like a salt mist from seawater, which would be cleaner and possibly actually produce a stronger effect because of the nature of the salt particles. And that you could target this at areas of unpolluted clouds in certain parts of the ocean where they'd be most susceptible, and you'd get this highly magnified reflective effect. And that in doing that, in these sort of few parts of the world where it would work best, by brightening 10 to 20% of marine clouds, or say the equivalent of 3 to 5% of the ocean surface, you might offset a doubling of CO2 or several degrees of warming by doing this. And so that's one approach to this kind of rapid cooling, if you like, that scientists are thinking about, that's related to an observed effect. And so this quality or this marine cloud brightening approach has the characteristic that you talked about, that it's relatively temporary. So you have to do it continuously, lasts a few days, and otherwise if you stop, it stops. And it's also relatively localized, so it opens up theoretical possibilities that you might consider it as a way of cooling ocean water and mitigating climate impacts regionally or locally.
Like we would put some of these mist generators like off the I don't know where the hurricanes are generated that slam into the southeast coast of America all the time, like off the coast of Africa, but we could put some like somewhere over there and we would get less hurricanes or something like that.
Yeah, so the picture that I'm showing you is the Gulf Atlantic, and like one part of where the hurricanes form or traverse. And so in theory, what you might do is, engage in this technique in the months before hurricane season. So your goal is to cool the ocean surface temperatures, which are a big part of what increases the energy and the rainfall potential of storms. So this idea is very theoretical. There's been almost no research in it.
Yeah.
And similarly, there's a little bit of emerging research and similar idea. Could you cool waters that flow onto coral reefs? And you might have to do this in areas that are further out from the coral reefs, because coral reefs tend to be in places where there are no clouds. Mm-hmm. But your goal is to try to get those big currents of water that are flowing on and cool them off.
Uh-huh.
And so there was a little test, very little test, tiny little test of the technology that you might use down in Australia as part of their big program. I think it's an $800 million program to look at all possibilities for saving the Great Barrier Reef.
Okay. One thing that I think is interesting for you to comment on briefly is I think many people, and myself included, don't really have like a good intuition about how thick the atmosphere is. Like some people, like you look up and it's just like big open space, like maybe it goes on forever or something. And there's not really an intuitive sense of like how big the sky is or like how thick the atmosphere is. So like how thick is it, and how is it that, you know, I mean, yeah, put it into scale so it makes sense that like 7 billion humans could affect it in such like large scale ways.
We're going to talk about it a little bit differently because we're taught, because the things I'm talking to you about are different layers of the atmosphere. They apply to different layers. So the idea that I talked to you about here, marine cloud brightening, that's really looking at the troposphere, which is the lowest layer of the atmosphere, which are, when you look up, these are the clouds I see. And it's the cloud layer that's closest to Earth, going from sort of like 500 feet up to a couple thousand feet. And so in that layer, you may have the possibility of, especially over the ocean, of generating a mist from the surface, where the convection, like the motion of the air above you, kind of pulls the particles up into the cloud layer. And so you can do this kind of activity potentially from the surface, like from ships.
Yeah, so go ahead. Sorry, finish.
And it's why the pollution particles are getting sucked up into the clouds too.
Okay. Yeah, and so like, what is that in miles? Like, that's not even.
That's sub-mile, right?
Yeah.
That's still just sub-mile, I would say. I think maybe and so that idea, you know, happens at that low layer, sub-mile layer, visible eye layer, of stuff. And for the most part, what's being proposed in terms of like volume of material, or like when scientists are talking about brightening these clouds, they're talking about brightening them 5 to 7%. So it's not something that you would probably see as a human with your own naked eyes.
And it's also over the ocean.
And it's over the ocean, and it's something that would have a relatively modest effect on, you know, the light coming into the ocean below. So probably a relatively modest effect on the like local ecology, except for the cooling that it's created. So so in that way, it's, you know, potentially less invasive than people might think. Just to veer off a little bit from your question, where the risks are, because I think it's related to your question, where the risks are in a technique like this are really around the fact that you're creating these sort of concentrated areas of cooling. And those have the potential to move the circulation of the atmosphere and change weather patterns in ways that are hard to predict. And that's probably the biggest thing that people are concerned about with this idea. Now, if you like, I can talk about what people are proposing at the other side, the high end of the atmosphere.
Yeah, so I was about to ask you about stratospheric sunlight reflection. Go for that.
Yeah, because this is the one that most people who've heard about this have heard about. And it's the most kind of widely studied and talked about, partly because it's based on events that have occurred in nature. And so, so when Mount Pinatubo erupted in 1991, large volcanoes push material into the atmosphere, and very large ones can push material all the way into the outer layer of the atmosphere, the stratosphere, which I think starts at about 30 or 40,000 feet. And goes up for a few miles. So when particles reach the stratosphere, they get entrained and they can stay for a year or two. And when Mount Pinatubo erupted in 1991, it was powerful, and it pushed particles into the stratosphere that stayed there for almost 2 years. And it produced a measurable cooling effect in the entire planet of at least 0.5 degrees C, actually popped up closer to 1 degree C. And so this cooling effect was sustained. It was very clear and measurable. It lasted until the particles fell down to Earth. And it also produced a marked change in Arctic ice. So this is a graph that shows Arctic ice mass starting in the late 80s and going up till now. And you can see this sort of pop in the year after Pinatubo, where Arctic ice mass just recovered drastically. And so this cooling effect, where the particles reach the stratosphere, they immediately or very quickly get dispersed globally. So it's a global effect, but it may have an outsized effect on the Arctic, which warms and cools faster than the rest of the planet based on what's going on. So this idea, and there are some other examples in the volcanic record, is what led scientists, including the Nobel Prize-winning scientist who identified the ozone hole, Paul Crutzen, to suggest that one approach to offsetting the warming that's happening with climate change would be to introduce particles in the stratosphere that reflect sunlight directly, almost kind of like bedazzling the stratosphere, and that by increasing this reflectivity by just 1%, that you could offset a doubling of CO2 or several degrees of warming. Now, the particles that volcanoes release in this way are similar to the pollution particles on the ground. They're sulfates and they're precursors. And so these particles also have the property where they can damage the ozone layer. And they can also cause the stratosphere itself to heat up. And so that introduces risks that we don't understand very well.
Yeah.
And so that, so that's what people want to study. But one thing I'll show you, and then I'll let you throw some questions at me, Lucas, is there isn't very much research on this yet, but one of the earliest models was produced at NCAR that compared the course of global surface temperatures in a business as usual scenario in the NCAR global climate model versus introducing particles into the stratosphere starting in 2020, gradually increasing them and maintaining temperatures through the end of the century. And what you can see in that model representation is that it's theoretically possible to keep global surface temperatures close to those of today with this technique. And that if we were to go down this business as usual path, or have higher than expected feedbacks that took us to something similar, that's not a very livable situation for most people on the planet.
All right, so so we have sorry, what is the level, the atmosphere that we live in called again?
Well, so the one on the left is called business as usual.
No, sorry, I'm asking you a different question. The place where we're trying to make clouds, what is that called?
The troposphere?
Oh, the troposphere. Okay, so so you can intervene. You can intervene in the troposphere or the stratosphere. Yeah.
Yes.
And so these are the two interventions that there's like there's a large degree of uncertainty about, like, indirect effects and second and third order effects of these interventions, right? So they need to be studied because you're impacting a complex system which may have complex implications in different degrees of like at different levels of causality. But so like the high level like strategy here is that these things may be necessary if we're not able to reduce greenhouse gas emissions sufficiently. And so that's why we may be interested in it for mitigating some degree of climate change that happens or is inevitable.
That's right. There's a slight sort of twist on that, I think, where it's really about, if we can, trying to look at these dangerous instabilities and intervene before they happen or before they take us across thresholds we don't want to go. So it is what you're saying, but it's a little bit of a different shade, where we don't wait to see how our mitigation effort is going necessarily. What we need to do is watch the Earth system and see whether we're reaching kind of the red zone where we've got to bring the heat down in the system.
Okay. All right. And so what kinds of ongoing experiments are happening for studying these two kinds of interventions in climate change? The tropospheric and stratospheric.
Well, so the first thing I'll say is that the research in this field has been very taboo for most of the past few decades. So relative to the problem space, very little research has been done.
Okay.
And the global level of investment in research even today is probably in the neighborhood of $10 million a year. And that includes a $3 million a year program in China and a program at Harvard, which is really the biggest funded program in the world. So relative to the problem space and the potential, we're very underinvested. And the things I'm going to talk to you about are really promising, and there are prestigious institutions and collaborations, but they're still at what I would call a very seed level of funding. And so that's what I'll say. So the two kind of most significant interdisciplinary programs in the field, one is aimed at the stratosphere, and that's a program at Harvard, which is an interdisciplinary program called the Harvard Solar Geoengineering Program, and includes social science and physical sciences. But a sort of flagship of what they're trying to do is to do an experiment in the stratosphere. And in their case, they would try to use a balloon, which is specially crafted to navigate in the stratosphere, which is a hard problem, so that they can do releases of different materials to look at their properties in the stratosphere as they disperse and as they mix with the gases in the stratosphere. And so for understanding, what we hope, and I think the people in the field, is that we can do these small scale experimental studies that help you populate models that will better predict what happens if you did this at a bigger scale. So the scale of this is tiny. It's like less than a minute of an emissions of an aircraft. It's tiny. But they hope to be able to find out some important things about the properties of the chemical interactions and the way the particles disperse that would feed into models that would help us make predictions about what will happen when you do this, and also what materials might be more optimum to use. And in this case, they're going to look at sulfates, which we talked about, but also materials that might have better properties. And so two of those are calcium carbonate, which is what we're used to in chalk, and diamonds. So what they hope to do is, start down the path of finding out more about how you might optimize this in a way to minimize the risks. Okay. And so any questions about that one, or shall I talk about the cloud?
Yeah, so let's talk about clouds now.
Okay. So yeah. The other effort is on the other side of the United States. This is an effort that's based at the University of Washington, which is one of the top atmospheric science institutions in the country. It's a partnership with Pacific Northwest National Labs, which is the Department of Energy Lab, and PARC, which many of your community may know is the famous Xerox PARC, who has since developed expertise in aerosols. So at the University of Washington, they're looking to do a set of experiments that would get at this cloud brightening question. And their scientific research and their experiments are classified as dual purpose. So meaning that they are experiments about understanding this climate intervention technique. Can we brighten clouds to actively cool climate? But they're also about getting at the question of what is this cloud aerosol effect? What is the accidental effect of emissions having? And how does this work in the climate system more broadly? So what they're proposing to do is build a specialized spray technology. So one of the characteristics of both efforts is that you need to create almost a nano mist of particles, like 80 to 100 nanometers, very consistently at a massive scale. And so it turns out that that hasn't been done before. And so that's this sort of, how do we generate this massive number of tiny droplets of materials of salt particles from seawater or, calcium carbonate particles. And some retired physicists and engineers in Silicon Valley took on this problem about 8 years ago. And they've been working on it for 4 days a week in their retirement for free, for the sake of their grandchildren, to invent this nozzle that I'm showing you, which is the first step of being able to generate the particles that you need to study here. And so they're in the phase right now where, because of COVID, they've had to set up a giant tent and do indoor spray tests. And they hope next year to go out and do what they call individual plume experiments. That's the picture that you can see of the little ship generating the plume. That's like one ship traversing the cloud. And then eventually they would like to undertake what they call a limited area field experiment, which would actually be 10,000 square kilometers, which is the size of a grid cell on a climate model. And that would be the minimum scale at which you could actually potentially detect a brightening effect.
Yeah, I guess, maybe it makes sense on reflection, but I guess I'm kind of surprised that that so much research is needed to figure out how to make a nozzle to like make droplets of aerosol or of whatever.
Well, yeah, I think I was surprised too. It turns out, I think, for certain materials, and again, because you're really talking about like a nano mist.
Yeah.
And so a lot of the applications for that are for like silicon chip manufacture, like asthma inhaler. And so here we're talking about 3 trillion particles a second from one nozzle, and an apparatus that can generate 10 to the 16th particles and lift it up in, a few hundred meters. And so it's not nuclear fusion, and it wouldn't necessarily have taken 8 years if they were like properly funded and it was a focused program. I mean, these guys, the lead, Armand Ugermans, funded this with his own money, and he was trading Biscotti, he's from Belgium, he was trading Biscotti for measurement instruments, over the course of the years. And so it's only recently in the past year or two where the program has gotten its first government funding, some from NOAA and some from the Department of Energy, very relatively small and more focused on the scientific modeling, and some money from private philanthropy, which they're able to use for the technology development. So, but again, going back to my comment earlier, this has been a very taboo area for scientists to even work in. And there have been no formal sources of funding for it. So that's made it go a lot slower. And the technology part is the hardest and most controversial.
All right.
But overall, as a point, these things are very nascent, and the problem we were talking about at the beginning, like predicting what the system is going to do, that in order to evaluate and assess these things properly, you need a better prediction system, because you're trying to say, okay, we're going to perturb the system this way and predict that the outcome will be better than the alternative.
Yeah.
So it's a tough, it's a tough challenge in terms of getting enough research in quickly.
All right. I hear you. That makes sense.
And the one other thing I'll say,
Yeah.
because people have, people have sort of propagated the idea that this is cheap and easy to do, and that it could run away from us very quickly. And that has not been my experience.
Run away in what sense? Like
In
everyone
the
just
sense
starts
that
doing it?
some billionaire could take a couple $2 billion and do it, or some little country could do it. The reality is,
as like even an attack, like
not necessarily an attack, but an ungoverned attempt to manage the climate system, from the perspective of one individual or one small country or what have you.
I see.
That's been a significant concern amongst, social scientists and activists. And I guess my observation working closely with it is, like, there are at least two types of technology that don't exist yet that we need.
Mm-hmm.
So we have a technology hurdle. These things scale linearly, and they pretty much stop when you stop.
Sorry, are the two technologies that we need the troposphere and the stratospheric interventions?
Well, specifically, I was referring to the aerosol generation technology.
Okay.
The thing I talked about just now.
Yeah.
And for the stratosphere, we probably actually need a new and different kind of aircraft.
Okay. Okay. And sorry, can you define aerosol?
Yes. So, and I'll caveat this by saying I'm not a scientist, so my definition may not be what a scientist would give you, but generally speaking, an aerosol is particles mixed with gases. And so, it's like a manifestation in air of a mixed blend of particles and gases.
Yeah. So
and
you have some small mist of whatever in the atmosphere, like it's hydrogen and oxygen and whatever else, and CO2. It's just like, yeah, that makes sense.
And so I'll often talk about particles because it's a little bit clearer. And what we're doing with these techniques for the most part is, dispersing particles in a way that they mix with the atmosphere and
become an aerosol.
Yeah. So I think that we have, like I would characterize the challenge we have right now is that we actually have a very low level of information and no technology. And these things would take, a number of years to develop.
Yeah, well, it's an interesting future to imagine the international politics of weather control, like negotiating whether to stop the hurricanes or to any of these more come in new powers we might get over the weather in the coming decades.
Well, so you bring up an interesting point, because as I've gotten into this field, I've learned about what's going on. And actually, there's an astonishing amount of weather modification activity going on in the world, and in the United States. And so,
like intentional.
Intentional,
yeah. Like I think I did hear that Russia did some cloud seeding or whatever it's called to stop some important event getting rained on or something like.
Yeah, and that kind of thing. Like if you remember the Beijing Olympics, where they seeded clouds to generate rain to clear the pollution. So that kind of localized cloud seeding type stuff has gone on for a long time. And of course, I'm in Colorado, like there's always been cloud seeding for snowmaking. And so what's happened though, in the Western United States, there's even an industry association for weather modification in the United States.
Wow.
That these, like what started out as especially snowmaking and a little bit of like attempt to affect the snowpack in the West has grown. And so there are actually major weather modification efforts in like 7 or 8 Western states in the United States. And they're mostly aimed at hydrology, like snowpack and water levels.
Well, like, is the snowpack for like a ski resort?
Well, it started, I believe, and I'm not an expert on the history of this, but I believe that snowmaking started out from the ski resorts. But when I say snowpack, it's really about the water table. And so it's about affecting the snow levels that generate the water levels downstream. And
Okay.
right, so because in the West, like a lot of our water comes from snow.
Okay. And so you want to seed more snow to get more water,
Correct. As a
and
drought
the government pays for that.
Right. And so I can't say for sure who pays.
Okay.
Because again, I haven't looked at, this is still an exploration for us, but there are fairly significant initiatives in many Western states. And like I said, they're primarily aimed at the problem of drought and hydrology. And so that's in the United States. And if you look at other parts of the world, like the United Arab Emirates they have a $400 million rainmaking fund. So can we make rain in the desert? And
All right.
you know, on the flip side of the coin, in Indonesia in January, this was in the news, they were seeding clouds offshore to induce rainfall offshore to prevent flooding. And they did that at a pretty big scale. In China, again this year or last year, they announced a program to increase rainfall in the Tibetan plain in an area the size of Alaska. And
Yes.
so we are starting to see, I think, around the world, and this activity would likely grow.
Yeah.
Where
sure.
you have, weather extremes and attempts to deal with them locally.
Yeah, that makes sense. And so are they doing this with what are they using to do this?
And again, I'm not super expert, but the traditional material is silver dioxide. Like that's what's proposed in the Chinese program, and many of like the rainmaking types of ideas. And so I think that there are two things we'll start to see. I think as climate extremes grow, there's pressure on politicians to act. Is growing interest in the potential for global mechanisms to kind of reduce heat, and bottoms up efforts that just continue to expand, that try to manage weather extremes in these kinds of ways.
All right. So so we have this tropospheric intervention by using aerosols to generate clouds that will reflect sunlight, and then we have the stratospheric intervention, which aims to release particles which do something similar. So how do you view the research and the project of understanding these things as fitting in with and informing efforts to decrease greenhouse gas emissions? And then also the project of like removing them from the atmosphere, if that's also something people are looking into.
Yeah, so I think they're all very related, because at the end of the day, from a silver lining perspective and a personal perspective, we see this as a portfolio problem. So we have a complex system that we need to manage back into a healthy state. And we have kind of a portfolio of things that we need to apply at different times in different ways to do that. And in that way, it's a bit like medicine, where, the interventions I'm talking about are sort of address, the immediate stressor.
Yeah.
But to restore the system to health, you have to address the underlying cause. Where we see ourselves as maybe helping bridge those things is that we are underinvested in climate research and climate prediction. So in the United States, our entire budget for climate research is about $2.5 billion. And so if you put that in perspective, that's like 1/10 of an aircraft carrier, It's half of a football stadium. It's, it's paltry.
Yep.
And this is the most complicated, computing intensive problem on planet Earth. So it takes massive supercomputing capacity and all the analytical techniques you can throw at it to try to reduce the uncertainty around what's going to happen to these systems. And so what I believe happened in the past few decades is the problem was defined as a need to limit greenhouse gases. So if you think of an equation where one side is the greenhouse gases going in and the other side is what happens to the system on the other end, we've invested most of our energy in climate advocacy and climate policy about bringing down greenhouse gases, and we're underinvested in really trying to understand and predict what happens on the other side. And so when you look at these climate intervention techniques like I'm talking about, it's pretty critical to understand and be able to predict what happens on the other side. And it turns out if you're looking at the whole portfolio, particularly if you want to blend in these sort of nature-based solutions that could bring down greenhouse gases, but they have complex interaction with the system, right? Like building new forests or putting nutrients on the ocean, that, that need to better understand the system and better predict the system, turns out we really need that. And it would behoove us to be able to understand and predict these tipping points better. So I think that where the interventions come in is to try to say, well, what does reducing the heat stress get you? What does it get you in terms of safety? What time does it buy you for these other things to take effect? And so that's kind of where we see ourselves fitting in. We care a lot about mitigation, about, let's move away from this whole greenhouse gas emissions business.
Yeah.
We care a lot about carbon removal and accelerating efforts to do that. And if somebody comes up with a magical way to do carbon removal at scale in the next 10 years, then we won't need to do what we're doing. Mm-hmm. But that doesn't look like a high probability thing.
Yeah.
And so what we've chosen to do is to say there's a part of the portfolio that is totally unserviced. Yeah. There are no advocates. There's almost no research. It's taboo. It's complicated. It requires innovation. That's where we're going to focus.
Yeah, that makes sense. So why don't let's talk a little bit about this taboo aspect. Maybe some number of listeners have some initial reaction, like anytime human beings try to intervene in complex systems, there's always unintended consequences or things happen that we can't predict or imagine, especially in natural systems. So how would you speak to or connect with someone who viewed the project of releasing aerosols into the atmosphere to create clouds to reflect sunlight? If someone was skeptical of that project and saw it as dangerous, how would you, what would you say to such a person?
Well, so I'll start out by saying I have a lot of sympathy with that.
Yeah,
I really do. And if we were, 30 years ago, if you're at a different place in the sort of risk equation, then this kind of thing really doesn't make any sense at all. And so if we're in 1970 or 1980, and someone's saying, look, we just need to economically tune, the incentives so that we phase greenhouse gases out of, the bulk of our economic system, that is infinitely smarter and less risky. So, and I believe that a lot of the principle and structure of how we think about the climate problem is based on that, because what we did was really stupid. Mm-hmm. And it would be the same thing as if the doctor said, well, you have stage 1 cancer, stop smoking, and you just kept on puffing away. So I'm very sympathetic to this. But again, coming from the primary concern that we're focused on are now our forward outcomes and the fact that we have this big safety problem. And so now we're in a situation where we have greenhouse gas concentrations that we have that are already there.
Yeah.
And we have warming and system impacts that are already there, and some latency built in that mean we're going to have more of those. And so that means we have to look at the risk-risk trade-off that based on the situation that we're in now, where we have conducted the experiment where we pushed all these aerosols into the atmosphere that mostly trap heat and changed the system radically. Like we did that. That was one form of, human intervention. That wasn't a very smart one.
Mm-hmm.
So what we have to look at now is we're not saying that we know that this is a good idea or that the risks outweigh the benefits outweigh the risks. But we're saying that we have very few alternatives today to act in ways that could help stabilize the system for a period of time. And so that's, for us, it's about how quickly can we generate information to assess and do a comparison. And the better that we can project what this warming is doing, and the better that we can optimize and predict what these interventions might do.
Yeah.
That'll give us some options in a place where we don't have them.
Yeah, that makes sense. And as a brief side note, if you're accidentally hitting your table, that might be something good to be mindful about.
Sorry.
No, it's all good.
I got emphatic.
Yeah, it's good for emphasis.
Got it. I'm not usually a table banger.
Only on issues you care about.
Right.
So, all right. So I'm interested in pursuing. Okay. Well, actually, let's stay on this point of people who might be skeptical of this. So can you enumerate what the main points are of detractors? So if someone is skeptical of this whole approach and thinks like, look, we just need to stick to removing greenhouse gases like by natural intervention, by building forests, and we need to reduce CO2 emissions and greenhouse gas emissions drastically, and to do anything else would be, just adding more danger to the equation. So what are the main points of someone who comes to this problem with such a perspective?
So I think you touched on two of them already. One is that the problem is actually not moving that quickly. And so we should be focused on things that are, more root cause, even if they take longer. And then the second one being, the fact that this introduces risks that are really hard to quantify. So, but I would say the primary objection that's raised by people like Al Gore, most of the advocates around climate that have a problem with this, is what they call the moral hazard. The idea that it gets put forward as a panacea, and therefore it slows down efforts to address the underlying problem. And so this is sort of saying like, even research in this stuff could have a societal negative effect, that it slows us down in doing what we're really supposed to do. And so that has some interesting kind of angles on it. One angle, which was talked about in a recent paper by Joseph Aldi at Harvard, and also was talked about with us by Republicans we talked to about this early on, was that, there's also the thesis that it could have the opposite effect, that the sort of drastic nature of these things could actually signal to society and to skeptics the seriousness of the problem. And so I did a panel with a bipartisan panel, and the Republican on the panel, who's a moderate guy, pro-climate guy, he said, when we Republicans hear these kinds of proposals coming from, people who are serious about climate change, it makes you more credible than when you come to us and say the sky is falling, but none of these things are on the table. And so I thought that was interesting early on. I thought it was interesting recently that there's at least an equal possibility that these things, as we look into them, could wake everyone up in the same way that more drastic medical treatments do, and say, look, this is very serious. So on all fronts, we need to get very serious. But I think in general, this idea of moral hazard, it comes up pretty much as soon as the idea is there. And it can come up, in the same way that Trump talks about planting trees. Almost anything can be positioned in a way that, could be attempted to use as a panacea. I actually think that one of the big moral hazards of the climate space has been the idea of winners and losers, because I think many more powerful people assume that this problem didn't apply to them. So I think
they're not in a flooding zone.
Right, or I can buy my bunker.
Or they can move to their bunker.
And I think that the people who put forward this idea of winners and losers in climate did that because they were very concerned about the people who were impacted first. And for the most part, they're the people who didn't cause the problem. They're vulnerable people.
Well, so there's,
But the mistake was in letting powerful people think that this wasn't their problem. And so I think that was a big societal moral hazard. And in this particular case, I'm optimistic that if we talk about these things candidly and we say, look, these are serious and they have serious risks, and we wouldn't use them if we had a better choice. It's not clear to me that moral hazard idea really holds, but that is the biggest reservation. And it's a reservation that means that many people very passionately object to research, that they don't want us to look into any of this because it sets off this societal problem.
Okay. That makes a lot of sense. These are just kind of like very side points, but it seems like it seems like moral hazard should be called something more like information hazard. Like the word moral seems kind of a little bit confusing here, because it's like, if people have the information that like this kind of intervention is possible, then bad things may happen. Like if they have this information, then bad things may happen. But like moral means like, I don't know, moral, like it has something to do with ethics rather than the consequences of information. So whatever. No one here has control over how this language was created.
Well, I agree with you. It's an idea that comes from economics originally, about like where the incentives are.
Okay.
But I think your point is well taken, because you're exactly right. Information is dangerous. It's a masked way of saying that information itself is dangerous, and that's a fundamental principle. And I find myself in meetings with advocates and around this issue having to say, look, our position is that information helps with fair and just consideration of this, that information is good, not bad. But I think you hit on an extremely important point, that it's a mass way of saying that information is too dangerous for people to handle. And our position is, information about these things is what empowers people all over the world to think about them for themselves.
There's a degree to which moral hazards or information hazards like lack like trust or confidence in the recipients of that information, which may or may not be valid, depending on the issue and the information. Here you argue that this information is necessary to be known and shared, and then people can make informed decisions.
That's our argument. And I think that there is a, I'll call it a marketing hazard, that, you know, people can take certain kinds of information and package it and market it in ways that are not useful. But that exists in all kinds of arenas. And so for us, we want to keep going forward and saying, look, let's generate information about this so we can all consider it together. But that's a, you know, I guess one thing I should say about that, because I was so shocked by it when I started working in climate, that this idea of moral hazard, it isn't new to this issue. It actually came up when they started looking at adaptation research in the IPCC and the climate community, and research in adaptation was considered to create a moral hazard. And so it didn't move forward. And one of the reasons that we, as a society, have relatively low level of information about the things I was talking about, like infrastructure impacts and the things you need to know for adaptation, is because there was a very strong objection to it based on moral hazard. And the same was true of carbon removal, you know, which has only recently come into consideration in the IPCC. So, you know, this information is dangerous idea because it will affect, you know, our motivation around this one part of the portfolio that we think is the most important. I would argue that that's already slowed us down in really critical ways. And so, you know, this is just another of those where we need to say, okay, we need to rethink this whole concept of moral hazard because it hasn't helped us.
Yeah, sorry. So what is the marketing hazard of discussing the infrastructure risk of climate change?
So this isn't the marketing hazard. This is the, you know, so going back, say, 20 years ago in the IPCC and the climate community, that there's this question of how much should we invest in looking at adaptation, how communities will adapt.
I see. How can we adapt?
And there was a strong objection to adaptation research because it was felt that it would disincentivize greenhouse gas reduction. And I think that's been a pretty tragic mistake because in my view, and probably people like you and me, well, if you had started research adaptation 20 years ago, you'd have much more information about what a shit show this is going to be and more incentive to reduce greenhouse gases, not less, because this is not very adaptable. But that was but the effect of that was a real dampening of any investment in adaptation research. And so like even adaptation research in the US federal system is relatively new because it was actively suppressed.
Yeah, I mean, the fear there is that like McAlpha Corp will come and be like, you know, it's okay that have all these emissions because we can just do this really cheap, we'll just make clouds later, right? And so they can do like, I mean, I feel like corporations have done extremely effective disinformation campaigns on scientific issues like smoking and other things. And so, I mean, I assume that would have been what some of the fear would have been with regards to adaptation techniques. And here we're putting stratospheric and tropospheric intervention as adaptation techniques, right?
Well, in what I was talking about before, I wasn't referring to this category, but the more traditional adaptation techniques like building, you know, dams
like
and
trees and
seawalls and planting new different types of vegetation and things like that.
Yeah.
Traditional adaptation, right, was considered a moral hazard. And so I was trying to say, like, I recognize that what I'm talking about in these climate interventions is fairly unusual. But even traditional adaptation techniques to protect people were suppressed. Now, in terms of what you're saying, I appreciate your point. And it's been raised to me before that, oh, maybe oil companies will jump on this as a panacea for what they're doing. And so we talked to oil companies about it, talked to a couple of them, and their response was, we wouldn't go anywhere near this because we're not conceding that because it
Oh.
would be an admission that ties their, fossil fuels to warming.
Warming.
So they're much more likely to invest in carbon removal techniques and things that are more closely associated with the actual emissions than they are anything like this. So I think that for some of those
why?
things,
Sorry.
because they're not conceding that they created the warming. And they're certainly not
but if they're creating the carbon, and now they're like, okay, we're going to help take out the carbon, isn't that admitting that they contributed to the problem?
Yes, but they're not conceding that they, that they are that they are the absolute and proven cause of all of this warming.
Oh, so they like inject the like uncertainty that people will say like there's weather and like this is all just weather and like the earth naturally fluctuates and like we'll help take CO2 out of the atmosphere, but maybe it wasn't really us.
Well, and if you think about them as, they're legal fiduciary entities.
Mm-hmm.
And so creating a direct tie between themselves and warming is different than not doing that. So I think that.
Yeah, sorry, I don't see why taking CO2 out of the atmosphere versus like saying that you can make clouds to reflect sunlight like admits to any difference in degree of culpability for the problem.
Well, so, it might be worth asking around. This is how it was described to me by at least one major oil company, that, there's a fairly substantial difference between, them looking at greenhouse gases, which are kind of part of the, landscape of what they do, and then, the actual warming and cooling of the planet. And so, which they're not admitting to be directly responsible for.
All right. Okay, we'll leave it at that then.
We'll table that one.
Yeah. Yeah. Okay. And so the other just final.
I guess the punctuation I will say is for those listeners who are concerned about oil companies doing this, that really not happening. And so if you're concerned about there being someone doing it, this is definitely, we can't count on them to bail us out and cool the planet this way, because they're really, really not.
Yeah. And my last like quip I was suffering over while you were speaking at some point was, if listeners or anyone else are sick and tired of the amount of disinformation that already exists, like get ready for the level 5.0 conspiracy theories that are going to happen, like chemtrail 5.0, when we have to start potentially using these mist generators to create clouds. There could be even like significant social disruption just by governments undertaking like that kind of project, it would seem.
Well, that's where I think generating information and talking about this in a way that's well grounded is helpful. That's why you don't hear me use the term geoengineering. It's not a particularly accurate term, and it sort of amplifies triggers. Whereas climate intervention is a more accurate term, and it helps kind of ground the conversation in what we're talking about. The same thing when we explain that these are based on processes that are observed in nature, and some of them are already happening. So this isn't some big new sci-fi, we're going to throw, bombs at hurricanes or something. Just getting the conversation better grounded. I've had chemtrails people at my talks. I did a talk at the Interval Cafe, the Long Now. And I had a guy set up a tripod in the back and record it. And he was giving out these little buttons that had an airplane with a little trail coming out and a strike through it.
Yeah.
It was fantastic. And I had a really long conversation with him, and it's when when you talk about it in this way, it's kind of hard to argue with. The reality is that, there is no secret government program to do these things. And there are definitely no mind altering chemicals involved in any proposals.
Well, that's what you would be saying if there were mind altering chemicals in the,
right.
in the
Fair point. That's a fair point. So we tend to try to orient the dialogue at the sort of, 90% across the political and thought spectrum, and leave our 5%, churning.
Yeah. It's not a super serious consideration, but something to be maddened about in the future.
One of the other things I'll say with respect to the other side of the spectrum, kind of the climate denial, climate skeptic side of the spectrum, is because we work in the policy sphere in the United States, and so we have conversations across the political spectrum, that in a strange way, coming at the problem from this angle, where we talk about heat stress and we talk about these interventions, helps kind of create a new insertion point for people who are shut down in the traditional kind of dialogue around climate change. And so we've had some pretty good success, actually, talking with people on the right side of the spectrum, or people who are approaching the climate problem from a way that's not super well grounded in the science. To kind of start by talking about heat stress and what's happening and the symptoms that we're seeing and these kinds of approaches to it, and then walking them backwards into, well, and you absolutely positively have to take down greenhouse gases. So it has, interestingly and kind of unexpectedly created maybe another sort of pathway for dealing with at least parts of those populations and policy people.
All right. So I'd be interested in pivoting here into the international implications of this, and then also talking about this risk in the context of other global catastrophic and existential risks. So the question here now is, what are the risks of international conflict around setting the global temperature via CO2 reduction and geoengineering is the bad word, and climate intervention? So I don't know, there are some countries which may benefit from the Earth being slightly warmer or hotter. You talked about how there were no winners or losers. But there are winners, if it only changes a little bit. If it gets a little bit warmer, then parts of Russia may be happier than they were otherwise. They may be more accessible and available for agriculture. And so the international community, as we gain more and more efficacy over the problem of climate change and our ability to mitigate it to whatever degree, will be impacting the weather and agriculture and livability of regions for countries all across the planet. So how do you view this international negotiation problem of mitigating climate change and setting the global temperature to something appropriate?
So I don't tend to use the framing of setting the global temperature.
Okay.
It's not clear to us that, we're really, really far from having a fine grained management capability for this. So we tend to think of it more in the context of, preventing certain kind of disastrous events in the climate system. And so I think in that framing where you say, well, we can develop this technology where we have knobs and dials for creating favorable conditions in some places and not others, that would be potentially a problem. But it doesn't necessarily look like that's how it works. So it's possible that some places, like parts of Russia, parts of Canada, might for a period of time have more favorable climate conditions, but it's not a static circumstance. And so the problem that you have is, well, the Arctic opens up, Siberia gets warmer, and for a couple of decades, that's nicer. But that's in the context of these abrupt change risks that we were talking about, where that situation is just a transitory state to some worse states. And so the question you're asking me is, okay, well, maybe we hold the, we hold the system to where, Russia's happier in this sort of different state that they had. But, I think that the massive challenge, which we don't know if we can do, is just whether we can keep the system stable enough to prevent lots of these. And so the idea that you can, stabilize the system in a way that's different than now, but still prevents these like cascading outcomes, that's a pretty, like, I would say, not the highest probability scenario.
So go ahead.
And so I think that, but I think there's certainly validity in your question, which is this just makes everybody super nervous. And it is the case that this is not a collective action capability. One of its features is that it does not require everyone in the world to agree. And so and that is a very unstable, concerning state for a lot of people. And it is true that its outcomes cannot be fully predicted. And so there's a high degree of likelihood that everyone would be better off, or that the vast majority of the world would be better off. But there will be outcomes in some places that might be different. And so it's more likely, rather than people electively tuning the knobs and making things more favorable for themselves, just that, 3 to 5% of the world thinks they're worse off. And while we've tried to keep the thing more or less stable. But I think behind your question is, even the dialogue around this is pretty unnerving and has the potential to promote instability and conflict. And one of the things that we've seen in the past that's been super helpful is for scientific cooperation, lots of global cooperation in the evolution of the research and the science, so that everybody's got information. And then we're all dealing from an information base, or, where people can be part of the discussion. Because our strong hypothesis is, like, we're kind of looking at the edge of the cliff, or, down into the shit show, where we might not have so much disagreement that we need to do something, but we all need information about this stuff.
Right.
So we have we have done some work in SilverLining at looking at this, and how the international community has handled things better or worse when it comes to environmental threats like this. So our favorite model is the Montreal Protocol, which is both the scientific research and the structure that help manage what is many perceived to be an existential risk around the ozone layer. And so that was, that was a smaller, more focused case of, you have a part of the system that if it falls outside a certain parameter, lots and lots of people are going to die. And we have some really rigorous science we have to do to figure out where we can let that go and not let it go. And the world has managed that very well over the past couple of decades. And we managed to walk back from the cliff, restore the ozone layer, and we're still managing it now. And so we kind of see some similarities in this problem space of saying, we've got to be really, really focused about what we can and can't let the system do, and then get really strong science around what our options are.
Yeah, so
the other thing I'll say about the Montreal Protocol, in case people aren't aware, is it is the only environmental forum, environmental treaty that is signed by all countries in the world. And it is I believe, maybe the only environmental forum that has membership of all countries in the world. And so there are lots of aspects of that are a really good model to follow for something like this, I think.
Okay, so like there's the problem of runaway climate change where tipping like the destruction of like important ecosystems lead to tipping points, and that leads to tipping cascades, and without the reduction of CO2 we get worse and worse climate change where like everyone is worse off. In that context, there is increased global destability. So there's going to be more conflict with like the migrations of people and the increase of disease. It's just going to be a stressor on all of human civilization. But you know, if that doesn't happen, then there is this kind of later 21st century potential concern of more sophisticated, you know, weather manipulation and like weather engineering technologies, making the question of kind of, you know, constructing and setting the weather in certain ways as a more valid international like geopolitical problem. But that obviously being like secondary and less important. But you know, primarily the concern is just, you know, obviously regular climate change with the stressors and conflict that are induced by that. And then an important model for this is what you call the Montreal Protocol, which was effective in solving the ozone layer problem from, was it fluorocarbons? I don't even know what the word is. Is that right?
HFCs, hydrofluorocarbons. Yeah, there are other chemicals too. So those are mostly the refrigerant chemicals.
Okay, I see. All right.
But one thing I'll say to your point, just to clarify a little bit about weather modification and the sort of expansion of that activity. So I think that that's already happening and likely to happen throughout the century. And let's say that climate change were to move along a more smooth curved path, we would see more of that. And the escalation of that and the expansion of that is a problem. Not necessarily people using it as a sort of a weaponized idea, but as weather modification activities get larger, they have what are called telegraphic effects. They affect other places. So I might be trying to cool the Great Barrier Reef, but I might affect, you know, weather in Bali. Yeah. And if I'm China and I'm doing, you know, trying to do weather modification, the area is the size of Alaska, it's pretty sure that I'm going to be affecting other places. And if it's big enough, I can affect global circulation. So I do think that that aspect, like that's coming onto the radar now. And that is an international decision-making problem, as you correctly say, because that's actually in some ways a bit, even almost a bit of a harder problem than the global one, because we've got these sort of national efforts where I might be engaged in my own jurisdiction, but I might be affecting people outside. And I should also say, just so everybody's clear, that weather modification for the purpose of weapons is banned by international treaty, a treaty called NMOD. And it's actually, it arose out of US weather modification efforts in the Vietnam War, where we were trying to use weather as a weapon and subsequently agreed not to do that. Yeah. So it's not an illegitimate concern. Right.
Yeah, that's interesting. I mean, I've never really thought much about that, but that's interesting.
Right.
So let's see here. So wrapping up here on the like geopolitics and the political conflict around climate change. Like, can you describe to what extent there is gridlock around the issue? I mean, like different countries have different degrees of incentives. They have different policies and plans and philosophies. One might be more interested in focusing on industrializing, like to meet its own needs. And so it would deprioritize reducing CO2 emissions. It could be a poorer country, or it could be a country that just wants to industrialize further. So how do you view like the game theory and the incentives and getting international coordination on climate change when, yeah, we'd all be better off if this didn't happen, but like not everyone is ready or willing to pay the same price?
Yeah, so I'll speak to that in a couple of different sides, because I'm not an expert in all sides of this, but from what I understand, that a relatively modest price for carbon. So, I mean, the main issue that we have now is that we have this externality, this externalized cost that people aren't paying for the damage that they're doing. And so a modest, charge for that, for greenhouse gas emissions, my understanding is that a relatively modest price for carbon can set the incentives such that innovation moves faster, and you reach the thresholds of economic viability for some of these non-carbon approaches faster. And that I come from Silicon Valley, so I think innovation is a big part of the equation.
You mean like solar and wind?
Well, there's solar and wind, which are the traditional techniques, and then there are emerging things, which could be hydrogen fuel cells, it could be fusion energy, it could be, and there are really important things in the category of waste management, agriculture. It's not just energy and cars, right? These other areas that are big greenhouse gas emitters. And we're just not reaching the economic threshold where we're driving innovation fast enough, and we're reaching profitability fast enough for these systems to be viable. So with a little turn of the dial, right, in terms of pricing that in, you get all of that to go faster. And I'm a believer in moving that innovation faster means that the price of these low carbon techniques will come down. Mm-hmm. And you'll also accelerate offlining the fossil fuel or the greenhouse gas generating stuff. So I think that, it's not sensible that we're not, building in like a robust mechanism for having that price incentive. And that price incentive will behave differently in the developed countries versus the emerging markets and the developing countries. And it might need to be managed differently in terms of the costs that they face. But it's really important in the developing countries that we develop policies that incentivize them not to build out greenhouse gas generating infrastructure. However we do that, because a lot of them are at inflection points, right, where they can start building power plants and building out infrastructure. And so we also need to look closely at aligning policies and incentives for them that they just go ahead and build green. And it might be a little bit more expensive, which means that we have to help with that. But that would be a really smart thing for us to do. What we can't do is expect developing countries, who mostly didn't cause the problem, to also eat the impact in terms of not having electricity and some of the benefits that we have of things like, running water and basic needs. Yeah. So I think I don't actually think this is rocket science. I'm not a total expert, but I think what the mechanisms that are needed are not super complicated. Getting the political support for them is what the problem is.
And so a core solution here being increased funding into innovation, into like the efficacy and efficiency of renewable energy resources, which don't pollute greenhouse gases.
The R&D funding is key, right?
Yeah.
And I think in the US, we've actually been pretty good at that in a lot of parts of that spectrum. but you also have to have the mechanisms on the market side,
Uh-huh.
because where right now you have effectively fossil fuels being subsidized in terms of not being charged for the problem they're creating.
Uh-huh.
And sometimes we're subsidizing them beyond that, which is just bonkers. So, so basically we've got to embed the costs in the fossil fuel side of the damage that they're doing. And that makes the market mechanisms work better for these emerging things. And the emerging things are going to start out being more expensive until they scale.
Okay.
And so we have this problem right now where we have some emerging things, they're expensive. How do we get them to market? Fossil fuels are still cheaper. And so, that's the problem where it will eventually sort itself out, but we need it to sort itself out quickly. So we've got to try to get in there and fix that.
We got to push it from behind.
Right.
All right. So I'm mindful of the time here now. Just a few more questions if we might have some time for them to wrap up on.
Sure.
So let's talk about climate change in the context of global and catastrophic. Sorry, let's talk about climate change in the context of existential risks and global catastrophic risks. The way that I use these language is to say that global catastrophic risks are ones which would kill some large fraction of human civilization, but wouldn't lead to extinction. And existential risks lead to like all humans dying or all Earth originating intelligent life dying. And the relevant distinction here for me is that the existential risks like cancel the entire future. So there could be, billions upon billions or trillions of experiential life years in the future if we don't go extinct. And so like that is kind of this value that is being added into the equation of trying to understand which risks are the ones to pay attention to. So, I mean, you can react to this framing if you'd like. I'd be interested what you think about it, and also just how you see the relative importance of climate change in the context of global and catastrophic risks. Sorry, global catastrophic and existential risks, and how you see its interdependence with other issues. So I'm mainly talking about climate change as being in a context of something like other pandemics other than COVID-19, which may kill large fractions of the population, and synthetic biorisk, which in a sufficiently dangerous engineered pandemic could possibly be existential, or an accidental nuclear war, or misaligned artificial superintelligence that could lead to the human species extinction. So how do you think about climate change in the context of all of these very large risks?
Well, I appreciate the question. I think one of the characteristics that climate change has, many of the risks that you describe have the characteristic of that they are hard to quantify, and they're hard to predict. And some of them are sort of like big black swan events, like like even more deadly pandemics, or pandemics that arise from artificially engineered things. So so climate change, I think, shares that characteristic that it's hard to predict. I think that climate change, when you dig into it, you can see that there are analytical deficiencies that make it very likely that we're underestimating the risk. And so that's something I'd say, in the spectrum between sort of catastrophic and existential, we have not done the work to dig into the areas in which we are not currently adequately representing the risk. And so, so I would say that there's a definite possibility that it's existential, and that possibility is currently underanalyzed and possibly underestimated.
Can you expand that then?
So
like how could it possibly be existential?
Well, so I think there are two ways that it's existential, in the sense that, and I'm not an expert on like outlier conditions for the I watch a lot of sci-fi, and I like post-apocalyptic sci-fi and the different scenarios they have for they live in Cheyenne Mountain, or they live in a bubble, or they live on a, you know, a space orbit or whatever. I've watched all seasons of the 100, but I think that, you know, so I'll say I'm not an expert in like survivability and outlier conditions, but there were two, you know, if we just look at two phenomenon that are part of like non-zero probability projections for climate. One is this, like this example that I showed you where warming goes beyond like 5 or 6 degrees C.
Okay.
And the jury's pretty far out on what that means for humans. Remember, I talked to you about like the wet bulb phenomenon of the human body being able to survive.
Yeah.
And what we can engineer for that, and what it means about all the conditions of the land and the sea and everything else.
Yeah.
So the question is like, how high does temperature go?
Yeah.
And then what does that mean in terms of, you know, the population livability curve? And that part of what's involved in that, how high does temperature go, is the biological species and their relationship to the physics and chemistry of the planet.
Mm-hmm.
And so this concern that I had from Pete Worden at NASA Ames that I had never heard before talking to him was that, and he spent time looking at sort of planetary conditions in other places too, is that at some point in the collapse of biological life, particularly in the ocean, you have a change in the chemical interactions that produce the atmosphere that we're familiar with. So for example, the biological life at the surface of the ocean, the phytoplankton and other organisms, they generate a lot of the oxygen that we breathe in the air. Same with the forests. And so the question is whether you get collapse in the biological systems that generate breathable air. Now, if you watch sci-fi, you could say, well, we can engineer that.
Yeah.
You know, and that starts to look more like engineering ourselves to live on Mars, which you know, I'm happy to talk about why I don't think that's a solution.
Yeah.
But so I think that, you know, it's certainly reasonable for people to say, well, could that really happen? There is some non-zero probability that that could happen that we don't understand very well, and we've been reluctant to explore. And so I think that, you know, my challenge back to people about this being an existential risk is that the possibility that's an existential risk in a nearer term than you think may be higher than we think. And the gaps in our analysis of that are concerning.
Yeah, I mean, the question is like, do you know everything you need to know about all of the complex systems on planet Earth that help to like maintain the like small bandwidth of conditions for which human beings can exist? And the answer is like, no, I don't. And then the question is like, well, like how likely is it that like climate change will perturb those systems in such a way that it would lead to an existential catastrophe? Well, it's like non-zero, but besides that, I don't really have I don't know.
Well, and one thing to look at that I think everyone should look at who's interested in this is the observations of what's happening in the system now.
Okay.
And how they compare to the projections. And so what's happening in the system now are, you know, collapses of some biological life, changes in some of the systems that are indicative that this risk might be higher than we think.
Has the planet, go ahead.
And so if you look at things like, I think there was, you know, research coming out that estimates that we may have already lost like 40% of the phytoplankton on the surface of the ocean. So much so that the documentary filmmaker who made Chasing Coral was thinking about making a documentary about this.
About phytoplankton.
Yeah. And phytoplankton, I think of it as the API layer between the ocean and the atmosphere. Like it's a translation layer. It's really important. And so, you know, those are the kinds of things. And then I go to my friends who are climate modelers and they're like, yeah, phytoplankton isn't well represented in the climate models. There are over 500 species of phytoplankton, and we have 3 of them in the climate models. And so you look at that and you say, okay, well, there's a risk that we don't understand very well. So from my perspective, we have this a non-zero risk in this category. I'd be happy if I was overstating it and if it was really, really low. Okay. But it appears to me that it may not be.
Yeah. Okay, so that's all new information and interesting. So in the context of the existential risk community that I'm most familiar with, like climate change is like the way in which it's said to potentially lead to existential risks is by like destabilizing global human systems that would lead to the actualization of like other things that are existential risks. So like if you care about nuclear war or synthetic bio or pandemics or getting AI right, that's all a lot harder to do and control in the context of a much hotter Earth. And so the other question I had for you, speaking of hotter Earths, has the Earth ever been 5°C hotter than it is now? Like while mammals have been on it?
So I'm not an expert on paleoclimate conditions, especially the question of mammals. Hasn't been that hot while humans have been on it.
I see.
But I'm not expert enough to know as far as the mammal picture. I'm going to guess probably yes. The issue so I want to touch on the first points that you were making too, but about the societal cascade that might be existential. But on this question, the issue that we have, and I'm actually gonna show one more chart.
Yeah, let's do it.
Just to be super, super clear about, the problem. The problem with the warming isn't just whether or not the Earth has ever been this warm, but it's the pace of warming. Yeah. And so if you look at over the past, just the past couple thousand years, how far and how fast we're pushing the system, that normally when the Earth goes through its fluctuations of temperature, and you can see in the past 2,000 years, like it's been small fluctuations, but over the, hundreds of thousands, millions of years, it's been bigger. But it's happened over very long periods of time, like hundreds of thousands of years, which means that all the little organisms and all the big structures are adapting in this very slow way. And in this situation where we're pushing it this fast, there's just the natural adaptation, is very, very low. You have species of fish and stuff that can move to different places, but it's really not, it's happening so fast in Earth system terms that there's just no adaptation happening.
That's right. That makes sense. Yeah, I mean, I was just asking because if mammals had gotten through a long period of it being, 3 to 5°C hotter, then maybe that'd be good news for us.
Sorry, I'm having a little technical challenge here, trying to get back to you. Can't seem to escape out of my.
You're trapped in your presentation?
I'm trapped in my presentation. I don't know what to do. There we go. But to your other point about, climate change setting off existential threats to society in other ways, I think that's very true. And that climate change is likely to heighten the risk of like nuclear conflict on a couple different vectors. And it's also likely to heighten the risk that we throw biological solutions out there whose results we can't predict.
Yeah, and the meltdown of nuclear reactors.
For sure, yeah. So I think one of the facets of climate change that might be a little bit different than like runaway AI is just that it applies stress across every human and every natural system. And so that could pop, where you guys kind of look at existential pop threats, like things that could pop into a sudden catastrophe, it's got a number of ways in which it could drive pop threats like that.
Yeah, I see. Yeah, we're on spaceship Earth, and yeah, sometimes there's things that we can't see, but right now we're like driving towards a meteor field, and we're arguing about when to turn this steering wheel and how hard, because flying in this direction is convenient for now, something like that.
That's right. We overestimate our force field.
Yeah, we'll have to we'll reroute power from force field to.
That's right.
To change directions. Yeah. So this last point here then on climate change contextualized in this field of understanding around global catastrophic and existential risks. FLI views it as itself as being a part of the effective altruism community, and many of the listeners are effective altruists. And 80,000 Hours has come up with this this simple framework for thinking about what kinds of projects and endeavors you should take on. And so the framework is just thinking about tractability, scope, and neglectedness. So tractability is just like how much you can do to actually affect the thing. Scope is how big of a problem is it? How many people does it affect? And neglectedness is like how many people are working on it. So you want to work on things that are highly tractable or tractable, that have a large scope and that are neglected. So like, I think there's a view or the sense of climate change is that, from our conversation, it seems very tractable. If we can get human civilization to coordinate on this, it's something that we can, do a lot about. I guess it's another question on how tractable it is to actually get countries and corporations to coordinate on this. But the scope is global, and would in the very least affect our generation and the next few generations. Possibly, and it seems to not be neglected relative to other risks. You might disagree about that. Like maybe one could say that it's neglected relative to how much attention it deserves. But so I'm curious to know how you would react to this tractability, scope, and neglectedness framework being applied to climate change and in the context of other global catastrophic and existential risks.
Well, so firstly, I'm a big fan of the framework. I was familiar with it before, and it's not dissimilar to the approach that we took in founding SilverLining. And so where I think this issue might fit into that framework depends on whether you put climate change all in one bucket and treat it as not neglected, or you say in the portfolio of responses to climate change, of which we have a significant gap in terms of ability to mitigate heat stress while we work on other parts of the portfolio, that part is entirely neglected. And so I think for us, it's about having to dissect the climate change problem. And we have this collective action problem, which is a hard problem to solve, to ultimately move industrial and other systems away from greenhouse gas emissions. Mm-hmm. And we have the system instability problem, which requires that we somehow alleviate the heat stress before the system breaks down too far. And so I would say in that context, if your community looks at climate change as a relatively slowly unfolding problem, which has a lot of attention, mm-hmm. then it wouldn't fit. If you look at climate change as having some meaningful risk of, catastrophic to existential unfolding, in the next 30 to 50 years, and not having response measures to try to stabilize the system, then it fits really nicely because it's not, it's so underserviced that I represent the only NGO in the world that advocates for research in this area. And so, so it depends on how your community thinks about it, but we look at those as quite different problems in a way.
So the problem of, for example, adaptation research, which has historically been stigmatized, but we can apply this framework to this and see that if that you might get like a high return on impact if you focus on supporting and doing research in adaptation technologies, which would be the tropospheric or stratospheric interventions, like the cloud brightening.
So most people don't include these techniques under the banner of adaptation, just so we're clear,
okay,
like
sure. What does this count as then?
Climate intervention.
Climate intervention. Okay, so climate intervention technologies then being neglected.
That's right. And so I think that what's interesting to me and the people that I work with on this problem is that these climate intervention technologies have the potential to have very high leverage on the problem in the short term.
Yeah.
And so from a philanthropic perspective or an activist perspective, oftentimes I'm engaged with people who are looking for leverage. Like, where can I really make a difference in terms of supporting research or policy? And, I'm in this because I came from tech into climate looking what is the most underserviced, highest leverage part of the space. And I landed here. And so I think that, if your criteria that it's underserviced and potentially high leverage, then this fits pretty well. It's not the same as, addressing the longer term problem of greenhouse gases.
Yep.
But it has very high leverage on the stability risk, in the next 50 years or so.
Yeah, that's right. That makes sense. So if that's compelling to some number of listeners, how would you suggest that someone, what is your recommendation for action or participation for such persons if you think that, like, okay, this climate intervention stuff is compelling, and if I'm taking a portfolio approach to my impact or altruism and I want to put some of it into this, how do you recommend they do that?
Well, so it's interesting timing because we're just a few weeks of launching something called the Safe Climate Research Initiative, where we're funding a portfolio of research programs in the space to try to help catalyze it forward. So what we do at SilverLining is try to help drive philanthropic funding for these, high leverage nascent research efforts that are going on, and then try to help drive government funding and effective policy so that we can get resources moving in the big climate research system. So for people looking for that, when we launched the Safe or when we started talking about the Safe Climate Research Initiative, we were agnostic as to whether, if you want to give money to SilverLining for the fund or you want to donate to these programs directly. So we interface with most of the, mature-ish programs in the United States and quite a few around the world, mature and emerging. And we can direct people based on their interests, where they're alumni, where the, parts of the world, there are opportunities for funding really high caliber things, Latin America, the UK, India. And so we're happy to say, you can donate to our fund, and we're just moving through like getting seed funding to these programs as we can, or we can help connect you with programs based on your interests in different parts of the world that you're in, technology versus science versus impacts. So that's one way. For some philanthropists who are aware of the leverage on government R&D and government policy, SilverLining's been very effective in starting to kind of turn the dial on government funding. And we have some pretty big aspirations, not only to get funding directly in assessing these interventions, but also in expanding our capacity to do climate prediction quickly. So that's another way where, you can fund advocacy, and we would appreciate it. So happy to
accepting donations.
we're definitely accepting donations.
Uh-huh.
We're definitely happy to connect people or be a conduit for funding research directly.
All right. Just looking here. So all right, so let's end on a fun one here then. You mentioned that so we were talking a little bit before we started about your Visit Planet Earth picture behind you, and that you use that as a message against the colonization of Mars. So. Well, why don't you think Mars is a solution to all of the human problems on Earth?
Well, let's just start by saying, I grew up on Star Trek, and so the colonization of Mars and the rest of the universe is appealing to me. But as far as a solution to climate change, or an escape from it, just to level set, because I've had serious conversations with people. I lived for 12 years in Silicon Valley, spent a lot of time with the Long Now community, and people have a passion for these, for this vision of living on another planet, and the idea that we might be able to, move off of this one if it becomes dire. Yeah. The reality is, and it goes back to education that I got from very serious scientists, the problem with living on other planets, it's not an engineering problem or a physics problem, it's a biology problem. Mm-hmm. That our bodies are fine-tuned to the conditions of Earth, radiation, gravity, the air, the colors. And so we degrade pretty quickly when we go off planet. And that's a harder problem to solve than building a spaceship or a bubble. And so that's not a problem that gets solved right away. And we can see it from the conditions of astronauts that come back after a few years in orbit. It's just not great. And so the kinds of problems that we would need to solve to actually have like quality of life, living conditions on Mars or anywhere else are going to take a while, longer than what we think are the 30 to 50 year instability problem that we have here on Earth. And we are so, finely tuned to the conditions of Earth, like the Goldilocks sort of zone that we're in, that it's a really, really hard thing to replicate anywhere else. And so it's really not very rational it's actually a much easier problem to solve to try to repair Earth than it is to try to create the conditions of Earth somewhere else.
Yeah, so I mean, these things might not be mutually exclusive, right? So I mean, it really seems to be a problem of like resource allocation. Like it's not one or the other. It's like how much are we going to put into each? And so,
well, it's less of a problem of research allocation, I think, than of time horizon.
Well, I meant resource allocation.
Or sorry, resource allocation than time horizon. So I think that the kinds of scientific and technical problems that you have to solve to meaningfully have people live on Mars.
Oh yeah, that's a harder problem.
That's beyond a 50-year time horizon.
Yeah.
And our concern is that the climate instability problem is inside a 50-year time horizon. So
yeah, that's right.
So that's the main issue, is that over the long haul, there are advanced technologies and probably bioengineering things we need to do, and maybe engineering of planets that we need to do for that to work.
Yeah.
And so over the next 100 or 200 years, that would be really cool, and I'll be in favor of it also.
All right. Yeah, I think.
but for now, this planet is the spaceship that we have.
Yeah,
as you said.
Yeah.
And really, it's the theme of ours that here, this is the spaceship that we have. All of the people are on it, and failure is not an option.
All right, that's an excellent place to end on then. I think both you and I share the science fiction geek gene. About getting to Mars, but we'll have to potentially delay that until we figure out climate change. But hopefully we get to that. So yeah, thanks so much for coming on. This has been really interesting. I feel like I learned a lot of new things. There's a lot here that I think probably most people who are even fairly familiar with climate science aren't familiar with. So I just want to offer you a final little space here. If you have any final remarks or anything you'd like to say that you feel like is unresolved or unsaid, just any last words for listeners?
Well, for those people who've made it through the entire podcast, thank you for listening and being so engaged and interested in the topic. I think that apart from the things we talked about previously, it's heartening and important that people from other fields are paying attention to the climate problem and becoming engaged, particularly people from the technology sector and certain parts of industry that bring a way of thinking about problems that's useful. So I think there are probably lots of people in your community who, may be turning their attention to this or turning their attention to this more fully in a new way, and may have perspectives and ideas and resources that are useful to bring to it. The field has been quite academic, more academic than many other fields of endeavor. And so I think, what people in Silicon Valley think about in terms of, how you might transform a sector quickly or a problem quickly is, presents an opportunity. And so I hope that people are inspired to become involved and, and become involved in the parts of the space that are, maybe more controversial or easier for people like us to think about.
All right. And so if people want to follow or find you or check out SilverLining, where are the best places to get more information or see what you guys are up to?
So I'm on LinkedIn and Twitter as @KellyWanser, and our website is silverlining.ngo. SilverLining, all one word, no S at the end, .ngo. And you can find the majority of the information about what we do is there. And feel free to reach out to me on LinkedIn or on Twitter, and or contact Lucas, who can contact me.
Yeah, all right, wonderful. Thanks so much, Kelly.
All right, thanks very much, Lucas. I appreciate it. Thanks for taking so much time.
Yeah, you too. No, thank you. All right.